Alright, this video is going to go over inverse functions. To know about inverse functions, we first need to understand the concept of one-to-one functions. You'll see me abbreviated as 1-1 for one-to-one functions. Alright. Given two x values, a and b, with them not being equal, then a function f of x is 1-to-1 if the two x values not being equal implies the corresponding y values are also not equal, meaning each x value will map to a different y value. Another way to think about this is by using the contrapositive, meaning you flip this conditional statement and you change the inequalities to equalities, meaning if the y values are equal, then that would imply that the corresponding x values are also equal. It's not a two-way conditional statement. For instance, the y values being not equal does not imply that the x values are also not equal. Likewise, the x values being equal does not imply that the y values are equal. It only works one way on each of these. I have a couple of examples on the next slide to illustrate this. Alright, for this example, it's a two-part example. Decide whether each function is 1-to-1. Let's start with part A. Part A, it might be easier if we use the contrapositive. Take two x values, two random x values, a and b. We're going to show that their y values, if we plug in their y values and set them equal to each other, this will lead us to the conclusion that the x values also have to be equal. Alright, so if we start with the first part of the contrapositive, f of a is equal to f of b. Alright, f of a, that means everywhere there's an x in f, we plug in a, so it would be minus 4a plus 12 equals f of b, that would just be negative 4 times b plus 12. So now, if you subtract 12 from both sides, you would have minus 4a is equal to minus 4b divided by negative 4. And that tells you that the y values being equal would imply that the x values are equal. So, in this instance, f of x is 1-to-1. Alright, so now for part B. Part B, we can start with the contrapositive again. F of a is equal to f of b. So that would be square root of 25 minus whatever the random x value is, squared, a squared, is equal to 25 minus the other random x value, b squared. Now, to undo a square root, you have to square it. So let's square both sides to keep the equation equal. So that would just give us 25 minus a squared is equal to 25 minus b squared. So now, if we subtract 25 from both sides, that would give us, those would cancel out, so it would be minus a squared is equal to minus b squared. Divide both sides by -1, that tells you that a squared is equal to b squared. So, if you want to take the square root to both sides, that means that square root of a squared, which is positive or negative a, is equal to positive or negative b. So that means positive a is equal to positive b, or positive a is equal to negative b. Likewise, opposite of a is equal to b, opposite of a is equal to opposite of b. Likewise, you see here, the x values do not necessarily have to be equal in order for the y values to be equal. So it's not 1-to-1. Alright, the next thing we're going to learn about is something called the horizontal line test. It says a function, pretty much if you have the graph of a function and if you can draw a horizontal line and that horizontal line only crosses the graph once, then it's 1-to-1. Alright, here's a couple of examples of using the horizontal line test. Alright, based on the graph are these two graphs 1-to-1. Notice for part A, you have a horizontal line here that crosses the graph in 3 different locations. So part A is not 1-to-1. But if you notice for part B, it's a linear function. No matter where you draw a horizontal line through a linear function, it will still cross the graph at most once. So this one, part B, is 1-to-1. Now, we discussed the horizontal line test and one-to-one functions because that ties heavily into inverse functions. But before we go over how to tell if two functions are inverses, let me go over the concept of what an inverse function is by giving you an example. Alright, given these two functions, f of x equals 2x plus 1 and g of x equals 1/2 x minus 1/2. Let's first compute f of 3. So, f of 3, you plug it into our function. Instead of 2 times x, it would be 2 times 3 plus 1, which gives you 7. Now, let's take that output value and plug it into our other function. Plug it into g of 7, so instead of 1/2 times x, it would be 1/2 times 7 minus 1/2. So that'd be 1/2 times 7, which would be 7/2, minus 1/2. 7 halves minus 1/2 would be 6 halves, which would give you 3. So you see how this first function contains the point 3, 7, but the other function, it took the output and you got back what you started with originally, the 3. So the other function contained the point 7, 3. That's kind of what inverse functions do. The range value of f became the domain value of g, and the range value of g became the domain value of f. That's what inverse functions do. The domain of one function becomes the range of the other, and the range of one value becomes the domain of the other. So, what they'll do is they'll end up swapping the coordinates. You plug in one value, get out the output. If you plug that output value in as the input value of the inverse, you'll get your original value back. So now, to tell if two functions are inverses, this ties into our earlier work in composition of functions. Alright, so if you compose two functions f and g together, if you compose g with f and you get x, also if you compose g with f of x and you get x, then two functions are inverses. Now we're going to work a couple of examples illustrating this. Well, when I said a couple examples, I meant one, maybe two, three, four, I don't know how many. We're going to start with this one. If let functions f and g be defined in this way, is g the inverse function of f? And likewise, another way you could ask that is f the inverse of g. To start that, you have to compose them together, f of g of x. Remember, that's the same as f of g of x. So, remember, g of x is just the cubed root of x plus 1. So that means everywhere there's an x in f, you plug in g. So instead of x to the third, it'd be cubed root of x plus 1 to the third minus 1. Alright, raising a cubed root to the third power undoes that, so you're just left with x plus 1, and then minus 1. X plus 1 minus 1, the 1 and the minus 1 cancel out, so you're just left with x. So the first part checks out. Now you have to do g of f of x. Remember, that's the same as saying g of f of x. I don't know why I put the parentheses in front of the g. That's the same as saying g of x to the third minus 1, because f of x is x to the third minus 1. So that means, now, everywhere there's an x in g, you have to plug in the entire function f. So instead of the cubed root of x plus 1, be the cubed root of x to the third minus 1. Then you have this plus 1 on the end. The minus 1 and the plus 1 cancel out, so you have the cubed root of x to the third. Cubed root of x to the third is just x. Since composing the functions both ways gives you x, then the answer to our question is yes. Alright, here's a three-part example on finding the inverses of one-to-one functions when they're listed in ordered pairs. It says find the inverse of each function that is one-to-one. Now part A, it says let's first determine if it's one-to-one. And remember, a one-to-one function means each x value corresponds to a different y value. Now, part A, if you notice here, you have two different x values and the same y value. So part A is not one-to-one. Remember, normally for functions, we said if to tell something's a function, we don't want the x values to repeat. For it to be a one-to-one function, we don't want the x values or the y values to repeat. So for part B, none of the y values repeat, none of the x values repeat, so it is one-to-one. So for part B, the inverse, which we denote g inverse, you just flip the x and the y's, because remember the domain of one function becomes the range of the inverse, and the range of our original function becomes the domain of our inverse. So instead of 3, 1, it contained the point 1, 3. Instead of 0, 2, it contained the point 2, 0. Instead of the point 3, 2. Or instead of the point 2, 3, it contains the point 3, 2. And instead of the point 4, 0, it contains the point 0, 4. Alright. So for part C, it says the table in the margin shows the number of days in Illinois that were unhealthy for sensitive groups for selective years using the air quality index. Let f be the function defined in the table with the years forming the domain and the number of unhealthy days forming the range. Alright, so none of the x values repeat, obviously, because they're listing different years, and none of the y values repeat either, so it is 1 to 1. So if that's the x and that's the y of our original function, then the inverse, well, first, that would correspond to the ordered value 2004, 7, 2005, 32, etc., etc. Likewise, that can correspond to the ordered pair 2009, 13. So, for the inverse of this function, you just flip the domain and the range. So it would be 7, 2004, 32, 2005, 8, 2006, 24, 2007, 14, 2008, 13, 2009. And that's supposed to be a squiggly bracket on the end. Alright, now that we've discussed how to find the inverse of functions when they're listed as ordered pairs, let's go over how to find inverses of functions whenever we're given the equation. Alright, here are the steps, or the general steps to finding the inverse. Rewrite y as f of x, because it's easier as far as notation goes just to use y instead of f of x. So after you do that, you would swap all the x's and y's, like change all the x's to y's and all the y's to x's. You solve for y, and then after you solve for y, you just replace y with f inverse. Before we start with the examples, just note, do not confuse this f inverse with the exponent -1. F inverse of x is not the same as 1 over f of x raised to the first. It is not. Do not do that, because you would get the problem wrong. Alright, so here's a 3-part example. It says determine whether each equation defines a one-to-one function. If so, find the equation of the inverse. Alright. For part A, it's a linear function. We already established in an earlier example that a linear function is 1 to 1. In fact, it was in the second part of example 2. So, part A is 1 to 1, so let's start by rewriting f of x just y. So y equals 2x plus 5. We switch the x's and the y, so x is equal to 2y plus 5. And now we're going to solve for y. Subtract 5 from both sides, so x minus 5 is equal to 2y. Divide everything by 2. And you're left with y equals, or we can replace it with f inverse of x. It's equal to x over 2. Remember, x over 2 is the same as having 1 in front, so you'd rewrite it as 1/2 x minus 5/2. Now for part B, y equals x squared plus 2. If you recognize, that's an upward facing parabola. So there are infinitely many places where it would fail the horizontal line test. Since it's not 1 to 1, that means there is no inverse. Part C. Part C is a cubic function. Since it's x minus 2, that means it's shifted to the right 2, so it just looks like this. If you notice, that one would be 1-to-1. Because no matter where you draw a horizontal line on the graph, it only crosses 1, so it is 1-to-1. So for part C, let's start with rewriting it as y equals x minus 2 to the third. So now we swap the x's and the y's. So x is equal to y minus 2 raised to the third. Now we solve for y. Since we're raising the right side to the third power, you need to take the cubed root of both sides, because the cubed root and the raising to the third power will undo each other, so you have cubed root of x is equal to y minus 2. So if you add 2 to both sides, the minus 2 and the plus 2 cancel out, so you're left with y equals, or we can say f inverse of x equals cubed root of x plus 2. Alright, suppose I give you the equation of a rational function and I tell you to find its inverse. You do it the same way. Like for this function, as long as we don't include positive 4 in the domain, it would be a function. And we're already told it's 1-to-1, so let's find the inverse. You can start by rewriting it with y. So y equals 2x plus 3 over x minus 4. And then you swap the x and the y's. X is equal to 2y plus 3 over y minus 4. And then you solve for y. Now, you need to get rid of the denominator, so you multiply both sides by y minus 4. Because that would cancel out that y minus 4. So, if you multiply the left side by y minus 4 and then distribute, you have y times x, or xy minus 4x, equals 2y plus 3. So now, let's get the y terms on the same side. Because when solving a rational function, after you swap the x and the y's, you multiply by the denominator, get the y terms on the same side, and then you go from there. So we moved all the y terms to the left-hand side, so we need to move all the non-y terms to the right. Those would cancel out, so we're left with x times y minus 2y equals 3 plus 4x. Now, from here you can factor out a y, so you're left with x minus 2 equals 3 plus 4x. So, if you divide both sides by x minus 2, you're left with y equals, or we can simply rewrite f inverse of x is equal to 3 plus 4x all over x minus 2. Alright, now I want to illustrate how the graph of f of x compares to f inverse. So here's an example of two random functions f and its inverse f inverse. If you notice, when you graph a function f and its inverse, they're simply reflections over the line y equals x. So if you graph two functions and they are mirror images across the parent linear function, then you can't really conclude without doing the algebra, but it would pretty much appear that they are inverses. Alright, so here's one last example, and also we're going to graph the function and its inverse. It says let f of x be equal to the square root of x plus 5, with x being greater than or equal to 5. Find the inverse. Now, if you remember, since it's x plus 5 and x being greater than or equal to negative 5, what this means on the graph, remember, square root functions always look like this. They always look like the top half of a sideways parabola. And the domain would be all x values greater than or equal to 5. Because if you picked any value less than -5, say -6, you'd get a negative number underneath the radical. So the domain for this would be all the x values from -5 to infinity, and the range would be all the y values from 0 to infinity. So now let's find the inverse. Let's replace the f of x with the y, so y is equal to the square root of x plus 5. Remember, our first step is always to swap the x's and the y's, so x is equal to the square root of y plus 5. Now, since we have the y underneath the square root, we need to square both sides. So if we square both sides, we have x squared is equal to y plus 5. And if we subtract both sides, if we subtract 5 from both sides, then we have left with y equals, or f inverse of x equals, the quadratic function x squared minus 5. If you were to graph this, it would start at -5 and go upward. So the domain remember, the range of our original function is equal to the domain of our inverse. So the domain would have to be from 0 to infinity, because the range of our original function was from 0 to infinity, so we'd only graph the right-hand side. And our range would be the set of all y values, so it would be from -5 to infinity. And here's a nice, neat picture of both our function f and the inverse graphed together. As you can see, our original function f of x, the square root function, is in blue. Our inverse, which is the right half of the quadratic, is it's either red or purple, I can't tell. But either way, if you notice, they are mirror images across the line, the dashed line y equals x. So that's how, so as you can tell from the graph, they do appear to be inverses.